We now come to what is often referred to as a very aesthetically significant property of the Fourier transform, which is called the duality. Duality refers to the fact that both the forward Fourier transform or the analysis and the inverse Fourier transform, namely the synthesis, are mathematically very similar though not identical operations. So, let us just write down these two expressions, very familiar to us by now already, but let us just write them down. X omega equals integral minus infinity to infinity. Here of course, the variable of integration is t equals minus infinity to infinity x t e to the minus j omega t dt, whereas we have x t equals 1 by 2 pi omega equals minus infinity to infinity x omega e to the j omega t d omega. In the first case, the integral is with respect to t, in the second case the integral is with respect to omega. In the first case, the integrand contains x t, the second case it contains x omega. In the first case, there is e to the minus j omega t, and here we have e to the plus j omega t. So, there is a change in sign. Apart from all this, of course, there is the multiplying factor outside 1 by 2 pi. All this is of course a very minor difference between the way you calculate the inverse transform and the forward transform. Thus, often if for a particular kind of function x t, you have already taken the efforts of evaluating the integral to find x omega, then if in a different situation you encounter an x omega which has the same form as the x t for which you already had the Fourier transform, then you could calculate the inverse transform of x omega from your knowledge of how you computed the forward transform of x t. Let me put it another way. Suppose for some x t you have evaluated x omega. Now, suppose in the omega domain you had the same function small x, that is to say you have x omega, then the similarity between these two expressions will be able to give you the expression for the inverse transform. Some function of t can be evaluated using your experience of this. In order to substantiate this further, let us carry out a simple exercise. Let us for example take x t, find its Fourier transform x omega, and then let us find the Fourier transform once again of x omega. In order to not confuse variables, we will now be clear that we are trying to find the forward Fourier transform of x omega using a new frequency variable which we will call say x omega dash. So, then what happens if we carry out a forward Fourier transform of x omega once again? It turns out that you get 2 pi x of minus t. This is the, if this is the Fourier transform of this and this is the Fourier transform, then this is what you get. In short, we have come from x t back to x t by carrying out two forward Fourier transforms or two Fourier analyses. First step yielded us x omega, and a further Fourier analysis of x omega has yielded 2 pi times x of minus t. This is interesting because we can continue this chain of events and take another Fourier transform, and this will give us 2 pi times. Now, recalling the properties we have already observed, x minus t being Fourier transformed will give us x of minus omega. This is the third in the sequence of Fourier transforms we have carried out on x t itself. Now, let us carry out just one more last Fourier transform, another f t, and what you expect to get is 2 pi x minus omega. Here, when we did it 2 steps previously, we got 2 pi x omega gave us 2 pi x of minus t. Now, this 2 pi is already there. So, what you will get is 4 pi squared x of t. That means, the 4 sequential applications of the Fourier transform on x t and the results will yield 4 pi squared x t once again after a cycle length of 4 steps. Alternately, you could easily see that if you carried out inverse Fourier transforms of x t at each step, it would be just going backwards through this same sequence of results that we already have. So, 4 pi squared x t subjected to a sequence of 4 inverse Fourier transforms would yield you x t. In short, if you started with x t, you normally apply a Fourier transform because it is already a time domain function, but if you applied an inverse Fourier transform on x t and did this over and over again, what you would finally end up with, at the first step you would end up with 1 by 2 pi x of minus omega, okay. And if you carried out another IFT, you would end up with 1 by 2 pi x of minus t. One more time, and you would get 1 by 4 pi squared x of omega, which subjected to one more inverse Fourier transform would give you 1 by 4 pi squared x t. So, you started with x t and ended up after 4 steps of inverse Fourier transformation with 1 by 4 pi squared x t. All this essentially uses the duality of the Fourier transform. The similarity, the high mathematical similarity between the forward and the inverse transforms, and this comes in useful in a lot of situations. For example, now we are going to study a new property of the Fourier transform called the modulation property. Where we will address the question of what is the Fourier transform of the product of two time functions. Suppose you had x t and y t, x t y t with respective transforms x omega y omega. Then we ask the question, what is the Fourier transform of x t times y t. Now, recall that we already know what happens if you have the convolution of two time functions in the time domain, then its Fourier transform has already turned out to be the product of their Fourier transforms. Now, we have a product of two functions, but this time in the time domain, and instead of carrying out a forward Fourier transform as we did, I mean instead of starting with the time domain as we did, we now have a product in the time domain instead of the frequency domain, and we want to find the Fourier transform of this product. By applying the duality property suitably, you can easily see, and I will not try to spend time on evaluating it here, that this comes to 1 by 2 pi x omega convolved with y omega. All right, more properties. There is something called Parseval's relation. That establishes a relationship between the energy in x t and the energy in x omega. They turn out to be proportional to each other with a scale factor of 1 by 2 pi that relates them. Now, the energy in x t is given by x t mod squared dt integrated over all time. This is the energy in x t. Now, let us find the Fourier, let us find what this comes out to be. This is nothing but minus infinity to infinity x t x star t, because it was mod squared x t dt. Now, x star t equals x star of minus omega. It does not equal it. It is the inverse transform of x star of minus omega. Let me just rewrite that part. D omega. Now, replacing omega by minus omega dash, this comes out to be equal to 1 by 2 pi integral minus infinity to infinity x star of omega e to the minus j omega t, or rather x star of omega dash e to the minus j omega dash t d omega dash. This has happened by setting the omega dash equal to minus omega. Now, we will use this over here and write integral minus infinity to infinity mod x t squared dt equals integral minus infinity to infinity x t into x star omega dash, fine, e to the minus j omega dash t d omega dash dt. Now, we can reverse the order of these integrals. Sorry, there is a 1 by 2 pi, this is all 1 by 2 pi, another integral minus infinity to infinity over here. This is what we have. We can exchange the integrals and get integral minus infinity to infinity 1 by 2 pi, of course outside, x star of omega times minus infinity to infinity x t e to the minus j omega dash t, there is omega dash here also, d t d omega dash, which yields 1 by 2 pi integral. Now, just calling omega dash omega, you can as well leave it as omega dash if you like, you get minus infinity to infinity. You have x star of omega over here, and the second integral inside is nothing but x omega. So, you get x star omega x omega, which is nothing but mod x omega whole squared d omega. So, we have that this equals this, which is what is called the Parseval's theorem. Now, this is the energy in any function x t, and if you have a function x omega, the energy in that is given by integral x omega mod x omega squared integrated over all omega. It turns out that the energy in x omega is related to the energy in x t through this factor 1 by 2 pi. That is essentially the statement of the Parseval's theorem. Next, what we will now deal with is a slight generalization of the Parseval's theorem, where of course the significance of energy no longer holds. Suppose you had integral x t y star t dt integrated for all time, which is the analog, the more generalized analog of x t x star t dt that we had. Then it turns out that its Fourier transform results in 1 by 2 pi integral minus infinity to infinity. This time of course, this was with respect to time, this is with respect to omega, x omega y star omega d omega. This is just a generalization of the existing Parseval's relation, which reduces to the existing Parseval's relation if you replace y t by x t. So, this is just the generalized Parseval's relation. In the same way, you can go around evaluating the Fourier transforms of the interactions between various functions. This is one example of an interaction between two functions x t and y star t. We want to find out the Fourier transform of x t y star t. Earlier we found out the Fourier transform of the product x t y t. Even before that we found the interaction, the convolutional interaction of two functions x t convolved with y t or x t convolved with h t. So, these are all interactions of various sorts. One very commonly used interaction is the correlation between two functions. Correlation is called the autocorrelation if you correlate the same function with itself with different shifts. It is called cross correlation if there are two different functions which are correlated with different shifts. So, the correlation in general between two functions, between say x t and y t, is a plot of the inner product of x t and y t minus tau or x t plus tau and y t evaluated against tau. That means, the inner product is evaluated like this. The correlation is given by integral t equals minus infinity to infinity x t x t plus tau y star t d t. This might look somewhat similar to convolution, it is not, because here we are integrating against t, and what we therefore get is, and also we are conjugating the second function. Now, if you evaluated this, the correlation of these two functions, and you wanted the Fourier transform of the correlation of these two functions, that is to say, you wanted over all tau, that is e to the minus j omega tau, tau equals minus infinity to infinity. This whole thing is a function of tau. The correlation itself is a function of tau, of the relative shift between x and y, and therefore, of this correlation function, if you evaluated the Fourier transform by putting d tau over here, what would you get? It turns out to be equal to x of omega y star of omega. Now, look at this as the Fourier transform of the correlation of two functions. That is one way of doing it, one way of looking at it. Suppose you looked at this just as the result of a convolution. Remember, if you convolve two functions, you get a product of Fourier transforms. So, suppose I ask you now, what are the two functions of time that ought to have been convolved to get this expression? That is not hard to see. This is a product of x omega and y star omega. What is the inverse transform of x omega? The inverse transform of x omega is x t, and the inverse transform of y star omega, what is it? Remember that y star t would give you y star of minus omega. So, y star of omega will give you y star of minus t. So, it is the convolution of y star minus t with x of t that is equivalent to correlating x t and y t. So, the correlation is simply equal to x t convolved with y star of minus t. Now, if you look at different textbooks on signals and systems, you will find that there are variations in the way in which correlation is defined. For example, I have said that it is the integral of x t plus tau y star t. Some others would put it as x t y star t plus tau. Some people will put it as x star t y t minus tau, and so on and so forth. There are various variations you get on this theme depending upon exactly the choice of the author, but the fundamental fact remains the same, that they are all correlations and they measure the similarity between two signals under different amounts of shift. If y t is replaced by x t, then you have what is called autocorrelation or the time autocorrelation. If y t is not equal to x t, this is when y t equals x t. When y t is not equal to x t, you get what is called the time cross correlation. One of the final properties of the Fourier transform that we will study is about what happens to the Fourier transform of a signal that is differentiated. So, differentiation. suppose xt has a transform of x omega, and we want to know what happens to the Fourier transform of something we denote by this d by dt of xt. In order to find this out, we shall use the synthesis equation. Xt equals integral 1 by 2 pi, of course, minus infinity to infinity x omega e to the j omega t d omega, and differentiate this equation with respect to time. On the left side you will get d by dt of xt, and the right side we will find has only one factor that depends upon t, and that is e to the j omega t. When that is differentiated against time, you will get j omega times e to the j omega t. So, you get in form, this expression is simply the Fourier transform of this quantity. That is to say, we can now claim that is just the inverse Fourier transform of this quantity, and so we can say that d by dt of xt equals j omega x omega. Essentially, this means that when you differentiate a signal, you simply multiply its Fourier transform by j omega. That means, by a imaginary quantity proportional to the frequency of the signal, to the respective frequency component of the signal. Now, having studied differentiation, let us now look at integration. The inverse of differentiation, as we know, is the running integral. So, this is the running integral, and we want to find the Fourier transform of the running integral of a signal if we know the Fourier transform of the original signal. Now, this requires first that we prepare the ground by making a few preliminary remarks. One of the final properties of the Fourier transform that we will study is about what happens to the Fourier transform of a signal that is differentiated. So, differentiation. Well, suppose xt has a transform of x omega, and we want to know what happens to the Fourier transform of something we denote by this d by dt of xt. In order to find this out, we shall use the synthesis equation. Xt equals integral 1 by 2 pi, of course, minus infinity to infinity x omega e to the j omega t d omega, and differentiate this equation with respect to time. On the left side you will get d by dt of x t, and the right side we will find has only one factor that depends upon t, and that is e to the j omega t. When that is differentiated against time, you will get j omega times e to the j omega t. So, you get in form, this expression is simply the Fourier transform of this quantity. That is to say, we can now claim that is just the inverse Fourier transform of this quantity, and so we can say that d by dt of x t equals j omega x omega. Essentially, this means that when you differentiate a signal, you simply multiply its Fourier transform by j omega. That means, by a imaginary quantity proportional to the frequency of the signal, to the respective frequency component of the signal. Now, having studied differentiation, let us now look at integration. The inverse of differentiation, as we know, is the running integral. So, this is the running integral, and we want to find the Fourier transform of the running integral of a signal if we know the Fourier transform of the original signal. Now, this requires first that we prepare the ground by making a few preliminary remarks. The point is this: when you differentiate a signal and get its derivative, as we all know very well, two quite different signals can have the same derivative, though they are themselves different. In order to illustrate this point, we will take a certain signal x t and then set x 1 t equal to x t, set x 2 t equal to x t, plus c, where c is some constant. Now, it is clear that d by dt of x 1 t equals d by dt of x 2 t, though actually x 1 t and x 2 t are not equal to each other. So, this is a fact that we must keep in mind when we try to integrate a function, find the running integral of a function and find its Fourier transform. So, now let me point out as the next step in preparing the ground a certain property of the Fourier transform. We have x t transforming to x omega. Now, a very interesting and very nice convenient feature we have is that x 0, the value of the Fourier transform at omega equal to 0 is simply equal to integral minus infinity to infinity x t dt. That is simply because if you want it to be explained, x t e to the minus j 0 t dt, and this after all equals 1, and that is how you get this. So, we have this property. Now, what we are going to do is this: given any signal, it can be divided into two parts. The part which has 0 average value and the rest, the average value. So, let me put it like this. Suppose you have x t, I will say that x t has 0 average value if x 0 equals 0. On this basis, we see that if you differentiate such a signal and comparing it, this is just another way of saying that there is no DC component in x t. So, going back to our two newly defined signals x 1 t and x 2 t, it turns out that if x t is 0 average, then dxt by dt equals dx1t by dt equals j omega x omega, right. Since x 2 t equals x t plus c dxt by dt dx 2 t by dt equals dxt by dt these two are the same thing, but then x 2 t x 2 omega equals x omega plus 2 pi c delta omega. Now, this is the only important thing that we need to keep in mind to go to the next step. All right. Now, consider the unit step u of t. Now, u of t is not 0 average. Since u of t equals 1 for t greater than or equal to 0, it has an average value or DC value of half. So, I will express u of t as a sum of a zero average component and a component which is the DC part. u1 of t plus half, where is simply equal to u of t minus half. So, this is what I have for u1 of t. So, u1 of t looks like this. This is u1 of t. Now, clearly, since it has a jump of unity at t equal to 0, du by dt of u1 of t equals delta t, which has a Fourier transform as we know of unity. Delta t's Fourier transform is 1. So, what is u1 of omega? By which of course, I mean the Fourier transform of u1 of t. u1 of t have a transform u1 of omega, then u1 of omega equals j omega times 1. Sorry, I am just going back by a second. Then 1, which is the Fourier transform of delta omega, equals j1 j of omega u1 of omega, so that u1 of omega equals 1 by j omega. But then there is also the other component, and so we are just a little away from finding the Fourier transform of u of t. Now, u of t equals u1 of t plus half. So, u of omega equals u1 of omega plus the Fourier transform of half, which is 2 pi into half into delta omega, which is just pi delta omega. That is to say, u of omega equals 1 by j omega plus pi times delta omega. So, this is what we have. This is the Fourier transform of the unit step. Now, how does this help us to integrate functions or to find the running integral of a function? Very easy. You will probably recall that to find the running integral of any x of t, one has to simply convolve x t with the unit step. That is to say that integral minus infinity to t x tau d tau for any x is nothing but x t convolved with ut, where u is the unit step. Given this fact and given our favorite convolution theorem, we can immediately say that the Fourier transform of this side must just be the product of the respective Fourier transforms here. So, this is equal to just a second. Let me call this as say yt. Then you have y of omega equals x omega multiplied by u of omega, which is equal to x omega by j omega plus pi x omega pi delta omega. This is what you get. But note that pi delta omega is always 0 except at omega equal to 0. So, we can simplify this. All right. Now, one final question: does this all tie up properly? We found we had x1 t equal to x t, where x t was taken to be a 0 average signal, and therefore, x 0 was 0. And then we had x2 t, which had an additional DC component of c. Now, will it turn out under the analysis we have done that both of them, when differentiated, since both of them will differentiate to the same function, will the Fourier transforms be the same? What is x1 omega? X1 omega equals x omega x2 omega will contain x omega, but it also contains a DC component fine. Now, if I differentiate these two functions, I really ought to get the same answer. That is, if I differentiate the two time functions and using the results we have obtained, find the Fourier transforms of the derivatives, do I get the same answer? Let us see. For the first case, I will get dx1 t by dt transforms to j omega x1 omega equals j omega x omega. For the second case, I will get d x2 t by dt equals j omega x omega plus there is a second term j omega 2 pi c delta omega. But then both these should have been the same. Are they the same? What I mean to say is j omega, the derivative, the Fourier transform of the derivative of d of x2 t must be equal to the Fourier transform of the derivative of x1 t. But then here we just got j omega x omega, whereas here we got j omega x omega plus this function, this additional term over here. So we really have to check if j omega 2 pi c delta omega is 0. Consider this function, because delta omega is a factor. We will just call this, say, some f of omega. We will call this f of omega, because delta omega is a factor in f omega. F omega equals 0 for omega not equal to 0. Because j omega is a factor, or more precisely because omega is a factor in f omega, f omega equals 0 at omega equal to 0. Hence, f omega is identically 0. Hence, the Fourier transform of dx1t by dt equal to j omega x omega equals the Fourier transform of dx2 t by dt.